Welcome to this explainer. Today we're diving into the fascinating and honestly kind of terrifying evolution of how human engineering absolutely conquered distance. We're looking at a trajectory of technological escalation that totally rewrote the rules of human conflict. Think about it. For centuries, warfare was literally limited by how far a soldier could throw a spear or a cannon could hurl an iron ball. Fast forward to today, we've got weapons that travel at hypersonic speeds, cross the globe in minutes, and unleash the literal power of the sun. It's an incredible journey from ancient fire arrows to intercontinental ballistic weapons, and understanding this whole arc is absolutely crucial to grasping modern global security. Let's get right into it.
So, what exactly is the difference between a rocket and a missile? People throw these terms around interchangeably all the time, right? But militarily speaking, there's a really crucial distinction here. Getting this baseline vocabulary down is going to help us map out everything that follows.
Here's the short of it. A rocket is essentially just the engine, or a dumb projectile. It burns fuel to push itself forward, and that's pretty much it. A missile, on the other hand, actually has brains. Sure, it uses a rocket or jet engine for propulsion, but it also has an active guidance system to hunt down and steer toward a highly specific target. So, the golden rule to remember? Every missile uses some form of propulsion, but not every rocket is a missile.
All right, part one, from arrows to V2s.
Just look at this progression. We've gone from 10th century tools of burning powder strapped to arrows in China to William Congreve's iron case artillery in the early 1800s. But the real game changer? That hit in 1944 with Wernher von Braun's devastating V2 rocket during World War II. The V2 was this massive, uninterceptable leap in engineering that basically bridged the gap between traditional artillery and actual space flight. It literally laid the groundwork for the entire Cold War.
Moving right along to Section 2, Anatomy of a Guided Missile.
You can kind of think of a modern missile like a super lethal self-driving car in the sky. Effective guidance is everything, and it operates in this continuous four-step loop. First up, it's constantly tracking its prey using its sensors. Second, the internal computer is crunching the exact spatial math needed to intercept a moving target. Third, it sends those calculated inputs straight to the control systems. And finally, step 4, it physically steers. We're talking manipulating aerodynamic fins, shifting wings, or even vectoring the actual thrust of its engine exhaust to adjust its flight path on the fly.
Now, the eyes of these weapons totally determine how that first crucial tracking step happens. You've got active homing, where the missile actually emits its own radar to illuminate the target. Then there's semi-active homing, where an external source, like a mothership or ground station, paints the target with radiation. And then there's passive homing, which is completely stealthy. In passive mode, the missile just quietly tracks emissions, like heat or radio waves, that are naturally coming right off the target. No warnings, just impact.
Let's jump into Section 3, ballistic versus cruise missiles.
The contrast between these two is just incredible. Think of ballistic missiles like throwing a massive, hypersonic rock into space. They use incredibly powerful rocket stages to blast way up into the atmosphere, or even out of it entirely, and then they basically just coast unpowered on a predetermined arc, plummeting down onto their target at mind-bending speeds. Cruise missiles are a totally different beast. They are essentially robotic jet planes. Powered continuously by jet engines, they fly totally flat, parallel to the ground. They'll often hug the terrain just a few dozen meters high just to stay completely under enemy radar, navigating using internal maps and GPS. But hey, for shorter distances, militaries heavily rely on tactical missiles, and these are tailored to highly specific battlefield environments. It all depends on where they launch from and what they're meant to destroy. You've got your anti-ship missiles, which are often sea skimmers meant to avoid radar detection. You have anti-tank guided missiles built to punch right through heavy armor. Surface-to-air missiles are designed to clear the skies, and air-to-surface missiles give aircraft a standoff capability, meaning they can strike the ground safely from a distance. Every single one is purpose-built.
Okay, moving to Section 4, the nuclear age. 17 kilograms. To put that into perspective, that's about the weight of a medium-sized dog. But that seemingly tiny amount is the exact critical mass of weapons-grade uranium-235 needed to trigger a devastating nuclear chain reaction. The standard chemical forces we see in normal explosives, they simply do not even begin to compare to the unimaginable absolute power bound up inside atomic nuclei. And then came the terrifying scientific leap from fission to fusion, which changed the game entirely. Fission works by splitting heavy, unstable elements. That's what was used in World War II. But scientists pretty quickly figured out they could use a fission explosion as a mere trigger to actually fuse light elements, like hydrogen, together. These fusion weapons, what we call thermonuclear bombs, release energy literally 1 million times greater than conventional chemical explosives. It's just staggering.
30 minutes. That is the chilling reality of exactly how long it takes an intercontinental ballistic missile to cross the globe. Just think about that. If an ICBM is launched from the other side of the planet, national leaders have less than half an hour to detect that launch, verify it's not a glitch or a false alarm, make a massive decision, and execute a response. And the scariest part? Once an ICBM is in its boost phase and soaring into space, there is no recall button. You can't take it back.
Because an ICBM attack is absolutely final, superpowers adopted the doctrine of mutually assured destruction, or MAD. It's this incredibly cold, mathematical calculation of deterrence. MAD essentially hinges on the idea that if one nation launches a preemptive strike, the other side will definitely have enough surviving nuclear forces, maybe hidden deep in underground silos or lurking in untrackable submarines, to launch a totally devastating counterstrike. It stops anyone from launching first because doing so guarantees their own total annihilation. So we're left with this really fragile piece, built entirely on the promise of apocalyptic violence.
Which brings us to our final part, Section 5, Shielding the Skies. So how do you defend against all of this? Well, modern defenses span a pretty wild spectrum of technologies. Out on naval ships, you have the Phalanx close-in weapon system. It uses automated radar to literally throw up an impenetrable wall of 4,500 dense tungsten bullets every single minute just to shred incoming cruise missiles. For higher altitudes, systems like the Patriot PAC-3 use kinetic energy, they're basically shooting a bullet with a bullet, to smash into incoming ballistic missiles at blinding speeds. And if we're looking to the future, militaries have been experimenting with systems like the tactical high-energy laser to literally just burn incoming rockets right out of the sky using concentrated light. Straight out of sci-fi, right?
But, alongside those physical defenses, there's a whole other layer of shielding, and that is international law. Over 140 countries have participated in voluntary agreements and treaties to try and control the spread of these apocalyptic delivery systems. You have things like the Missile Technology Control Regime, which seeks to limit the export of tech that could deliver weapons of mass destruction. And of course, the Non-Proliferation Treaty remains a massive cornerstone of global efforts to stop the spread of nuclear warheads entirely.
So we leave you with this final, vital question to ponder. As things like hypersonic glide vehicles and advanced anti-satellite missiles take the global stage, this intense cat-and-mouse game of human engineering clearly shows no signs of stopping. But is the ultimate shield against this escalation found in perfecting our military technology? Or does our true safety rely on the delicate, enduring work of treaties and international diplomacy? The answer to that is probably going to define the entire security landscape of the 21st century. Thanks so much for joining us for this explainer, and as always, stay curious.